This is joint work with my previous internship supervisors, Dr. Haiyan Lin and Xiaohong Gao at ACT, and also my academic advisor, Dr. Wawa Chang. So in adaptive learning, we're interested in presenting contents to students based on their previous behavior. So our objective is to find out which topics the student has not mastered yet, provide tailored support and tailored contents to the student according to this. In the end, we want to help the student to achieve their learning goals faster. There are a lot of benefits of adaptive learning. First of all, if it's in an online learning environment, it's going to be cheaper than one-on-one tutoring. And also, it can cater to different students' needs because for students starting at different levels, they can be assigned different contents. Oxman and Wang presented in a white paper several key components of adaptive learning, namely the content model, which contains the information on what are the topics or skills covered in the curriculum and what are their structural relationships, the detailed learning tasks for the student, and also the operationalized definition of the learning goals and the outcomes. And we also have the learner's model, which is essentially our measurement model. It can be the measurement on the learner's progress, how they're doing on the curriculum, or also collateral information on the learner's learning styles or their engagement and other factors that might contribute to their learning outcomes. And lastly, we have the instructional model, which actually has the content and the module correspondence. This is the thing that connects the learners to the contents of the course. So in this part, it includes which are the available learning materials and how do they correspond to the skills in the curriculum. And also the adaptive routing rule, which is based on how the student is doing. How do we assign him or her to the next content? There has been long time advocacy for matching assessment and instructions, both in classroom learning and also in online learning learning. If we look at the existing adaptive learning routing methods, we can mainly categorize them into two categories. First is the rule-based method. These are relying on some if-then rules. For example, the n in a row rule. So if the student answers 3 questions correctly in a row, then we think the student has mastered this content and he or she can move on to the next. Or we can also have algorithm-based rules, which is using some models. We select and using some algorithms, we select the optimal content based on some kind of methods. And most of the existing ones are relying on probabilistic graphic models, maybe based on IRT or based on Bayesian knowledge tracing. A lot of the problems with the existing methods is that by using a IRT model, the assessment results cannot directly measure the learner's acquisition of specific contents, and a lot of times the routing relies heavily on data-driven methods to do the routing. So we can see that using the regular IRT models, there's a lack of assessment methods that can adequately assess the learner's progress and directly guide adaptive routing. And this is why we look into cognitive diagnosis models. So CDMs, or diagnostic classification models, are item response models that measure the examinee's mastery status on a set of skills, where we call them attributes. We usually denote them by a dichotomous vector called alpha, where each entry indicates whether the learner has, whether someone has mastered a skill or not. And the correct response probability on an item depends on the examinee's the acquisition of the attributes that the item requires, which is usually captured by a Q matrix. And the attributes measured in the CDM can have different structures. They can be parallel to each other, which means that you can learn skill 1 first or skill 2 first. They do not affect each other. Or they can also be hierarchical, in which case, if you want to learn a more advanced skill, you have to master one of the prerequisites first. There are a lot of advantages of using CDMs in the context of adaptive learning. First of all, it connects the 3 components. The skills in the CDM can directly correspond to the instructional topics or the contents covered in the course. And then every assessment item can map to a set of attributes. And also what the student knows or misses at a certain stage can directly be used to guide what he or she should learn next. Since usually CDMs uses experts' ratings on the instructional contents or also the items, it allows a theory-driven method for the design. And it also has item response theory model, which allows algorithm-based assessment, ability estimation, and also content routing. Under the framework of CDM, there has been a recent paper saying that the recommendation system for adaptive learning can often be seen as the Markov decision process, where we are trying to assign the student a learning content so that we can maximize the reward in some case, which in this case means we want to minimize the number of stages the student has to go through to reach the instructional goal. This is itself a very complex subject, but here, since our focus is on the measurement, we want to assume a relatively easy adaptive routing rule. So assume that the set of attributes we have in the curriculum follow a natural order of instructions. What this means is that the first few skills in the vector are more basic, and the later ones are the more advanced ones that might have the earlier ones as the prerequisite. Then we can use the following procedures. We start the learning with an initial assessment to obtain the attribute estimate of the students before any kind of learning. And then we go through the following judgments. Are all attributes measured as master for this student? If yes, it means that the student has already learned everything. He doesn't have to go through any kind of other instruction and he can go home. Otherwise, we want to select the first skill measured as not master for the student as the next learning target. And then after, for this part, we assign the student a learning module targeting this skill. So this can be instructional videos or slides, interactive exercises or games. And after the treatment, we want to use a post-learning assessment to update the attribute estimate of the student. We iterate this process all the way until all the skills are measured as master for the student. So for the post-learning assessment, it serves several purposes here. So first of all, we want to make sure whether the student has learned the previously instructed topic. If yes, it means that the student can go on to the next one. And otherwise, we want to find out why. So if the skill is measured as not mastered, we want to identify why by looking at if he or she is missing any kind of prerequisites to the skill. And also, we want to provide the learner's information that can be used for the subsequent routings. So in the case that the student is missing a prerequisite, we should route the student back to that prerequisite because he or she cannot learn the current skill without mastering the more basic one first. So just like any kind of CAT, it has a trade-off between the accuracy and the ease. If we have too few items in the post-learning assessment, then we cannot get the accurate results on how the student is doing, and we might route him or her to a content that he or she might already know, in which case it wastes the student's time and efforts. However, if we have many items, especially in the case of continuous assessment in the learning progress, where we have to update the attribute pattern after each stage of the learning, it can cause severe fatigue or boredom and also the interruption of learning for the student. So we want to develop an efficient post-learning test using CDCAT. So traditional cognitive diagnostic computerized adaptive testing combines CDMs and computerized adaptive testing to choose items that can optimize the overall attribute pattern estimation accuracy and efficiency. It can have relatively good performance, which is providing a good estimate of the attribute pattern without very long tests. However, suppose that in this case, we are only instructing the student on the first skill and the whole curriculum contains 10 skills. Then it doesn't make sense for us to give a complete CDCAT that measures all 10 skills after just learning the first, because we're pretty certain that the student doesn't know the later 9, and it's going to give them a significant larger number of items. So we want to have a post-learning CDCAT that focuses on a specific subset of the attributes, namely in this case, our instructional target skill, and also its prerequisites. Here are some notations for the item response model. So at time point n, we want to denote the target attribute by k sub n. And then we use the set k bar sub n to denote the attribute k sub n, so the target and also its prerequisites. And then later on, we denote all the skills that are previously measured as mastered, but unrelated to our current target as k tilde n. So we can see that these two sets do not have any kind of overlaps. And also by using different kind of subscripts and time points, and we can figure out that there are different kinds of notations for the attribute pattern at different time points and the different subsets of the attributes we're interested in. For example, for this one over here, we have the true attribute pattern of the student before the learning, so the entire pattern. And for this one over here, is the previous attribute pattern of the student, but only we're focusing on the subset of k tilde n, so we disregard all the other entries. And also we assume that in the post-learning CDCat, we only administer items that measure the target attributes, which is the target and its prerequisites. And also they do not measure attribute outside of the union of these two sets. And if we assume a deterministic input noisy AND gate item response model for simplicity, we can figure out the conditional probability of correct response given a subset, the target attribute and the prerequisites after learning over here using the conditional law of probabilities. And we can, using some mathematical derivations, then we can figure out that this is equal to this one over here. And at the end, this probability is something that if we have the learning model and we have the posterior probability of different attribute patterns before the learning, we can figure this probability out by using the Bayes rule. However, if we do not have any information on the transition probabilities from the previous stage to the later stage, then we do not have any information on this part, then something we can do is to have an unrealistic assumption that the learning outcome on this subset is independent of this part over here. And then we can reduce it to an approximation which is given over here. And then after obtaining the item response model, we can have a post-learning CDCat item selection rule. We want to start from choosing items maximizing the KL divergence between the student has learned the target skill versus otherwise. And this formula is given over here in the first top equation. And we want to use the minimum, a variable length test termination rule. So if the minimum test length is reached and the posterior probability that the target skill is acquired exceeds 90%, in this case the cutoff is arbitrary, we want to terminate this post-learning test. And then the student can proceed to learning of the next skill that he or she requires. On the other hand, if we are pretty confident that the student has not learned the target skill, we want to switch to measure why he or she is not learning it. And we want to focus our measurements on whether there are any missing prerequisites. In this case, we want to use the PWKL, so the posterior weighted KL information at the current estimate, which is given by this over here. And you can see that over here we're most interested in what is the exact pattern on this subset, so the target and its prerequisites. So in this case, it can help us find out which one prerequisite is missing. We're going to terminate the test either when the maximum test length is reached or the posterior probability of a specific pattern of attributes in the target skill and the prerequisites exceeds a threshold, say 70%. And after each stage, so far the measurement is focused only on the subset of skills. But after each stage, we do have to obtain a point estimate of the entire attribute pattern to be able to guide the subsequent learning and for some further computations. So the ideal way to do this is if we have a learning model where we know the transition probabilities from the previous stage to the later stage, we can obtain the posterior probability of different kinds of overall patterns based on what's the estimated pattern from the previous stage, the transition probability, and also the responses at this stage. However, in the case that the learning model is not known, we can approximate it by taking all of the most freshest, well, most recent responses on each of the attributes to obtain the posterior probability of each of the separate patterns. And then we can take the MAP as the point estimate of this. We conducted a simulation study in the case that the learning model is not known, using to evaluate the post-learning CDCat. We simulated a total of 500 items following the DINA model. And they have a total, so the test measures the curriculum covers a total of 10 attributes with a hypothetical content structure. We also simulated 1,000 hypothetical learners' initial attribute patterns. And we used the following procedures to do the simulations. At the initial time point when n is equal to 0, we administer the students with an initial assessment using a regular PWKL-based CDCat. and the test length is fixed at 10 items. And then we iterate the adaptive learning procedure by starting the learning from the first attribute measured as not mastered at stage n, and then simulate the learning corresponding using a logistic model, with the intercept being the overall difficulty to acquire this skill and penalties for missing prerequisites. And then after the learning, we use the post-learning CD-CAT to update the estimate of the attribute patterns at that stage, with a minimum test length of 3 items and a maximum of 10 items. We iterate this process until the alpha hat for all the subjects is the vector of 1s. So here's an illustration. The top figure is the hypothetical content structure we used. So the skills below, 1, 2, 3, and 4 are the most basic ones that do not have any kind of prerequisites. And the upper ones, 5, 6, 7, and 8, have some prerequisites contained in the set of 1 through 4. And then there are more advanced skills such as 9 and 10, which contain skills in the second tier as their prerequisites. And here is one of the learning trajectories of the student, so one of the simulated subjects. On the left column, it is the true pattern of the subject, and on the right, it is the estimates at each time stage. And the red numbers denote what is going to be the next instructional target. And you can see that it's always going to be the first 0 in the estimated attribute vector. So at the initial time point, we can see that the student's third attribute is measured as not mastered. So it's going to be the learning target at the next stage. We simulate the learning process on the third attribute, and etc. We iterate this process all the way until all of the attributes are measured as mastered. And here are some results of the simulation studies. For the post-learning CD-CAT, it achieves relatively high accuracy, with average Hamming distance between the estimate and the true across stages being 0.45, which indicates that on average, there's less than 1 skill that's measured incorrectly for all the subjects. And in terms of detecting whether the learning target is learned or not, the sensitivity and the specificity both exceeded 95%. And also, it did relatively well in terms of identifying the prerequisite pattern the true prerequisite pattern. And in terms of efficiency, the average test length of the subjects is relatively low. We can see that on average, only 3.74 items are needed for the post-learning CAT, and which means that this is only slightly higher than the minimum test length that we used in this study. And in terms of the adaptive learning design, out of the 1,000 simulated subjects, 978 had true attribute patterns that are all 1s at the end of the learning. And on average, the number of learning stages is 10 for the subjects, which means that they usually go through around 10 stages to reach the learning goal, which is everything is measured as mastered. Also, we can see that in the case that the initial assessment was not accurate, the algorithm here performed relatively well by correcting the initial assessment errors. So the figure here summarizes for some of the subjects who had 4 or more attributes measured incorrectly at the initial assessment, we can see that the Hamming distance between the true and the estimate pattern decreased very quickly for almost all of them. So as a summary, the proposed post-learning CD-CAT item selection and attribute estimation method can accurately detect the target attribute mastery with very few items. And when the initial assessment overestimates the learner on certain prerequisites, by using the post-learning CD-CAT, we can re-estimate the prerequisite mastery and then route the students back to the things that they should have learned at first. There are a lot of limitations of the study. So first, one of the largest limitations is that in the case with the absence of the learning models, we assume the independence between the target skill and the set k tilde n. And also, the routing rule that we used does not utilize the information from the learning model either, because we assume that we don't have information from this. And also, with the increase of the number of attributes, there might be computational burden in item calibration according to any kind of cognitive diagnosis model. So this is something that we want to solve if a certain curriculum contains, say, 20 or 30 attributes. And we also use arbitrary cutoffs for the for determining whether we should terminate the test or mastery or not in the variable length test, in which we can switch to using developing cutoffs that are corresponding to theoretical type 1 or type 2 error rates. And one of the future directions, which is something we're trying to interpolate and do right now, is to incorporate the information on the learning process to estimate the student's ability and to guide the post-learning CD-CAT, also to guide the adaptive routing. So if we assume that there's a hidden Markov model for the CDM, then we can use something analogous to the forward-backward method to estimate the posterior probability of a specific pattern based on the previous pattern, the learning model, and also the current responses, in which case we can utilize more information. And also, if we want the entire learning trajectory of the students, we can use the Viterbi algorithm to be able to do that if we have the learning model. And also, there can be more optimal decision rules developed for guiding the student to different contents using Markov decision processes. And here are my references, and thank you so much. Yes?
Just, this is a sort of maybe off-the-wall general question. In using these cognitive diagnostic models, you're assuming discrete learning.
Yes.
Do you have any evidence that, that these are categories versus the continua? Now there's a lot of research actually in personality clinical psychology that was done by Neil to try and work out statistical indicators to determine whether or not something is a continuum or something is made of discrete categories.
So like the taxometrics methods?
Okay. So I think you're assuming they're discrete categories.
Yes.
But do you have any evidence that they are? And is there any harm caused by assuming they're discrete if they're continuous?
Well, first of all, I guess it depends on the actual context that we have. And if the process is actually continuous, there are some loss of information if we assume they are discrete. But in the case that there are multiple skills, say like 10 of them, using multidimensional IRT, we might not be able to fully calibrate all the items and also to obtain a precise estimate of the students. So I think CDM in some cases is a compromise between, this is some kind of compromise where we can obtain some information on whether the student is doing well on a certain skill. Yeah, so I think it depends on the context.
Because ultimately, I'm going to be interested in, at some other meeting, I'll ask the question when somebody's analyzing real data. If there's any validity argument that you can make that this classification of someone into this particular category based on the CPM model has any, you can make a validity argument with external data to go over and show that that classification is actually leads to a correct inference.
Yep.
And so that ultimately that's where I'm hoping people will go with this. You can't, of course, tell in a simulation study, but later on, you're going to be classifying someone into a category and saying you've mastered this or you did not master this, and really have some other external evidence to say that that classification is actually true.
Yes, and I agree. And I've also seen some literature having polytomous CDMs, in which case the mastery can be categorized to different levels. Say you don't know anything, you know something, and then you have something more. In which case, I think in the education context, maybe what we eventually want is not just a theta value that's continuous, but sometimes we want to classify the subjects based on what level of mastery they have. So that's, I think, also a possibility.
Okay, good afternoon. My name is Zhuan Shang. I'm a PhD student in statistics at University of Minnesota. So from the beginning of this year, I have been working on this interesting project with Professor Chun Wang and Professor David Waite, and today I'm very glad to share it with you. So in this project, we are designing a multi-dimensional CAT for graded responses with domain balancing item selection using a real item bank. So first, for the item response relation, we assume a multi-dimensional graded response model. So there are two keywords here. Multi-dimensional is referring to the latent attribute. So take our study as example instead of, So take our study as example instead of measuring people with only one scale, we are interested in learning about people's health conditions from 3 different aspects. So another word is graded. It means the response has 2 or more categories, and they are ordered. So the item parameters are similar to the 2PL model, except we call the difficulty by boundary parameters since it stands for the separation of different categories. So the model assumes that the categorical distribution Y depends on the item parameters and latent attributes is like this. Should be conditioned on both A and B. So there's a typo here. So you can see that here if theta equals to BJ1, then the probability of Y equal to 0 and the probability of Y not equal to 0 are equally 1/2. So it should also be noted that in this model, theta A and B are all vectors with dimension P. So here is an illustration of the model with 4 categories. The probability of Y fell into each category is represented as a function of theta. We are able to make this plot because we assume the item is simple structured here. So simple structure means that the response is related to only one dimension of theta, and the x-axis is that dimension. So in other words, only one element of A is non-zero. So you can see that if item parameters are known, depends on the value of response, we can tell which interval theta would be more likely to fall onto, and we can have a maximum likelihood estimator. So in this project, we work with a real item bank containing 324 items, all simple structured. So thanks to the work of Shi Yang, the item parameters are well calibrated. We have 3 dimensions or domains, apply cognitive, daily activity, and mobility. So number of items from the domains are pretty close. So you can see 109, 106, and 111. So most of the items have 4 categories also. Also from the calibration, we have the covariance matrix of theta. In population, our goal is to build a good CAT. So here, good means better measurement with test length being controlled. And what we need is an item selection method and a stopping criterion. So for the item selection method, we consider the d-optimality based on Fisher information. When we go to select a new item, for each unselected, untested item in the bank, we compute the Fisher information matrix for all the tested items and the new items, given the current estimate of theta. And then we select the item that maximizes the determinant of the matrix. The idea is based on finding the item that lead to the maximal decrease in the volume of confident ellipsoid of MLE. There's also an A-optimality that minimizes the sum of sampling variance of MLE, which is achieved by minimizing the trace of the inverse information matrix. So we generate 1,000 theta here from the multivariate normal distribution and run a simulation study. If we use the average RMSE over the 3 domains at each item for the y-axis, and we can see that the optimality selection works good on this bank, and the RMSE drops faster. In this plot, the solid line is the optimality, and the dashed line is random selection. If our target average RMSE is say 0.3, the adaptive testing will achieve it for about 50 items, while the random selection will use about 100 or something. So the difference is actually quite large. However, if we plot it by domain, we have different stories. The difference between the dashed line and the solid line is huge from the very beginning of the test for the blue line of mobility and the green line of daily activity. However, for applied cognitive, there are basically no difference at the beginning of the test. Why? Because there are actually fewer items selected on that domain. The thing is, the information each item carries highly depends on the value of the discrimination parameter. And if we look at the distribution of A, the value from the red domain is simply smaller in general, so they will have less chance to be selected by the algorithm. If we think about the ellipsoid in 3 dimensions, the volume of the ellipsoid can be shrunk significantly if we just decrease it, decrease the length of the 2 axes and leave the 3rd one alone. So back to this plot, the advantage of adaptive testing on applied cognitive appears in the later part of the test, when number of items exceeds 60, and probably the good items from the other 2 domains are exhausted at that point. And then it does not make a big difference for us. Since in the designing of the test, ideally we expect to give each patient about 30 to 50 questions to answer. And we will have measurement, in that case, we will have measurement performance similar to random test for cognitive diagnosis. This is not acceptable for us. So that's why we use these constraint weights on item selection. We set the upper and lower bound for the number of items in each domain, and the weight is a product of F1 and F2. You can see if the domain is tested too much, F1 will be smaller and it downweights the domain. On the other hand, if it is tested insufficiently, F2 will be large, and comparing to other ones, of course, and there's a better chance that item from that domain got selected. So also for the simulation result, here the dashed line becomes the weighted optimality. After applying the constraint weight, we see it improves the overall performance only by a little bit, but the improvement is within our target range of test length. And if we look at the plot by the domain, the difference is more obvious. The weighted method does not sacrifice the other 2 domains by very much, yet it improves the measurement on applied cognitive significantly. So here we show the result of the full length test. We can see the RMSE decrease slower and slower throughout the test. It is for us to decide when to terminate the test. So that's why we need to decide on a stopping criterion. For stopping criterion, we consider the D rule. It stops the test when the observed information is gathered to a certain amount. It is an overall criterion that considers the 3 domains at once. Since we know there's some domain differences, we also consider the SE rule, which stops the test, which stops the selection from each domain separately based on the standard error. And we also set a maximum test length, of course. And if we look at the growth of the information defined in the D rule, we got a trace plot by subject. So here, x-axis is the number of items, y-axis is information. If we use the solid, you can see the information is increasing throughout the test. If we use the solid horizontal line as our stopping criterion, we see most of the patients will be stopped before they answer 50 items. However, some of them will never be stopped by this rule. Why? The truth is, for those people, we don't have good items to measure their attribute. If we look at the largest boundary parameters of the items, if the response is actually the largest grade, then we have evidence to believe that theta is greater than this boundary. But how large? We don't know. The largest boundary parameter turned out to be too small. The majority is below 0. The largest boundary parameter turned out to be too small for the applied cognitive and the daily activity. So for larger thetas on those domains, we simply do not have information to measure them accurately. They cannot be stopped by the D rule nor the SE rule for similar reason. So do we stop them all at the maximum test length? From the previous plot, we can see that the information for some of them are still growing, but for some, they stopped grow at a very early stage. So what is the point to give all of them the maximum test? So that's why we use this secondary T rule of theta convergence. So we call it T rule. If the theta has stopped moving for a few consecutive items, we stop the test. So for the compound rule in general, we first check the primary rule. If it is not satisfied, then we check the secondary rule. In the first 40 items, it is almost impossible to have this T rule satisfied, so we don't have to worry about early termination by the secondary. To be more illustrative, we can look at this plot of theta. Just a second. Yeah, we can look at this plot of theta. So in this plot, the red dots are stopped by the D rule, and the blue dots are stopped by the T rule. We can see the blue ones are typically in the corner with larger values in all dimensions since they are highly correlated. Okay, let's continue. So in simulation, to compare different methods, we consider 2 types of item selection method, 2 types of domain balancing, and 3 kind of stopping rules. We choose the upper and lower boundaries of the constraint weights according to the unit dimensional information function, or we can just use the constant one for all domains. And similarly for SE rule here, we can have the constant SE bound, or we can have different SE bound for different domains. So we summarize the result in terms of test length and other criterions. There's always a trade-off between the test length and the performance. So here, they have different test lengths. Generally, for longer test lengths, they will have better performance than smaller RMSE. According to a post-hoc analysis on the test length and RMSE, we have this 3-way interaction plot where we can conclude from the post-hoc analysis that for item selection, A optimality seems to have better performance in general, but it also have longer test length. So the difference between the A optimality and D optimal is small. It only have advantage when we use when we don't use any domain balancing constraint weight. But A optimality actually minimizes the sum of the variance of MLE directly. So it will have advantage if we compare them in terms of the average RMSE. So another conclusion we can draw is that for domain balancing with similar test lengths, the constraint weights can improve the performance significantly comparing to the unweighted selection, especially for the optimality. So the test lengths can be shortened if the boundaries are selected based on information. So, so the difference between this is the different constraint weights, and the constant constraint weight is in this test length comparison. So for stopping criterion, the information-based SE rule can be as good as the D rule, but the constant SE rule cannot be as good as those two. So the SE rule is actually not stable as the D rule in general, since it typically have large proportions stopped by the T rule, the secondary rule. So hence our decision of the combination of the method should be the D optimality with information criterion-based constraint weights and the compound D rule as stopping rule. So in summary, we are designing a CAT for multi-dimensional graded response model with real item bank for health measurement. We carefully applied a domain balancing item selection approach and a compound stopping criterion. The reason we are doing all this is to deal with the shortcomings in our item bank, like domain differences and lack of information at some point. So I guess life is easier if we have a perfect item bank, but that's not usually the reality. And sometimes the reality is more interesting. Okay, thank you for listening. Any questions?
This is actually a project that was supported by NIH R1 grant for 5 years, and we are in year 3, and all the items are written by the doctors, so that's why there are a lot of imperfections in the bank. And that's why we have so much trouble trying to design a better item selection method. So if the 3 scales are more balanced, then the D optimal or the A optimal item selection method will be sufficient. And because we have so imbalanced item bank, so we have to use this constraint weight and also have to decide upper bound and lower bound more informatively based on the capacity of the bank. So do you have any questions from the audience? I know this is the last presentation and you're already exhausted. So any comments, questions? All right, so that's all
Okay.
for today, this symposium, and thank you all for coming.